So in this video for the rate of chemical change module, we're going to talk about catalysts and enzymes, how they work and why they're important. Starting with catalysts. A catalyst is a substance that increases the rate of reaction but does not alter the products of the reaction and is chemically unchanged and not used up at the end of the reaction. It also lowers the activation energy of the reaction, and only a small mass of catalyst is needed to increase the rate of reaction. However, not all reactions have a suitable catalyst. As you can see from the table shown, different substances catalyze different reactions. This table describes three very common catalysts. So you can see that iron is used to catalyze the Haber process for making ammonia, which we will discuss in more detail at the end of this presentation. You've then also got vanadium 5 oxide, which is used to catalyze the contact process in making sulfuric acid, or manganese dioxide, which is used to catalyze the decomposition of hydrogen peroxide, which produces water and oxygen. If you look at the graph to your right, you can see that a catalyst allows an alternative reaction pathway that has a lower activation energy than the uncatalyzed reaction. This does not change the frequency of collisions. However, it does increase the frequency of successful collisions because a greater proportion of collisions now has the activation energy or higher. The effect of a catalyst on the activation energy is shown on the graph, which is also called a reaction profile. It shows how the energy of the reactions and products changes during the reaction. So now on to enzymes. Enzymes are biological catalysts that are very important for controlling reactions in the cells. Enzymes work in the same way as normal catalysts do, as talked about in the previous slide, and they're also very useful in industry. So if you take a look at the diagram shown, it just briefly explains how enzymes work as a catalyst. So the substrate will enter an enzyme's active site. Now, an enzyme has a very specific active site for a specific substrate. The enzyme and substrate will then bind, forming an enzyme-substrate complex. The enzyme catalyzes the reaction to produce an enzyme product complex. The products then leave the active site of the enzyme, and the enzyme is then ready once again to be reused for a substrate to reform an enzyme substrate complex and repeat the process over and over again. Now, while enzymes are really good catalysts, they do like to work under very specific conditions. So changes in things like pH and temperature can change their structure and therefore their ability to act as a catalyst. Okay, so enzymes are, like I said, important in industry. The use of enzymes allows some industrial reactions to happen at lower temperatures and pressures than traditionally needed. One example would be yeast, which is a single-celled fungus. The enzymes in the yeast are used to produce wine, beer, and other alcoholic drinks by fermentation of sugars. I have provided some other examples for you. You don't need to learn these. I just thought it would be a bit interesting. So you've got palatase, which enhances cheese flavour in foods. Lipopan, which is an emulsifier, mainly used in food production again. And penicillin amidase, which is used for the synthetic antibiotic production. Now, as I mentioned at the beginning, we are going to talk about the Haber process. Now, this is a really important example of how enzymes are used in industry. It is used to make ammonia, and ammonia is used in fertilizers, explosive dyes, and many other things. Now, it is a reversible reaction, as shown below. It uses an iron catalyst, pressures of about 200 atmospheres, and a temperature of about 450 degrees. Now, another important feature is that the unreacted nitrogen and hydrogen are both recycled. This saves money and increases the effective overall yield of the process. Now this diagram just shows a very simplistic view of how the process works. So as you can see at point 1 here, nitrogen and hydrogen enter the system. They are then compressed at point 2. The compressed hydrogen and nitrogen enter the system at point 3 and are passed over iron catalyst beds. This speeds up the reaction, producing the ammonia product. Unreacted nitrogen, hydrogen, and the ammonia product then enter the cooling tank at point 4. The ammonia is cooled down to a liquid and extracted. The unreacted hydrogen and nitrogen both pass up this pipe, go back into the compressor, and work their way through the system again. So there is no loss of reactants here. It is a continuous process.